но уже нет необходимости рассказывать, почему кибербезопасность на сегодня настолько важна. Многие из вас, я думаю, уже смогли за последние годы на своем опыте убедиться в том, что важность достаточно велика. И мне очень хочется надеяться, что вы убедились это на примере атак, которые все-таки не достигли своей цели и были отражены с помощью инструментов, продуктов Cisco. Итак, к форуму. В этот раз мы подготовили для вас особую адженду, особый форум. В чем особенности? Во-первых, в этом году высадился достаточно большой десант спикеров, не только из Украины, любимых уже вами и знакомых вам, но и из европейской команды. Это ребята, которые отвечают за продукты Stealth Watch, за продукты Cloud, это Umbrella, CloudLock, за продукты MP, ThreatGrid и наши друзья из компании Redware. Все они поделятся интересными докладами. Я уверен, многие из них для вас станут достаточно большим сюрпризом. Вторая вещь, которую мы подготовили, это сегодня в 10 часов, может быть, чуть позже, мы немного затянули начало из-за регистрации, но в 10 часов у нас здесь, на этой сцене, произойдет панельная дискуссия с некоторыми из вас. То есть выступят клиенты, это представители Национального банка, это представители Новой почты, это представители Приватбанка и Укрзалезницы. То есть здесь они смогут, вы сможете с ними поделиться, точнее, они с вами поделятся, и обсудят кейсы из своей жизни и примеры того, как кибербезопасность, что это в их жизни. Также очень важно, я думаю, многие из вас уже увидели стенды наших партнеров и дистрибьюторов в холле. Я очень прошу вас, подходите в перерывах, смотрите, что там. Там действительно очень крутые стенды, и ребята очень долго готовились. Для того, чтобы вам было интересно, мы подготовили очень много призов и сюрпризов. Многие из них, это такой, пока еще не будем рассказывать, но один из них хочу поделиться. Это будут крутые футболки с крутым принтом, которым мы выбирали всем офисом, и много других призов. Для этого вам нужно будет участвовать в опросах, в анкетах, отвечать на вопросы со сцены. По-моему, вам должны были рассказывать по поводу того, как пользоваться кахутом, где чего нажимать. В общем, я очень вам рекомендую на сессиях участвовать в этих мероприятиях, вы получите хорошие призы. И последнее. То, что хочется сказать, я уверен, что сегодняшнее мероприятие – это не просто образовательный ивент, это не просто прийти и послушать там умных дядей или послушать хорошие презентации. В первую очередь, мне хочется, чтобы вы воспринимали это мероприятие как инвестицию. Инвестицию в себя, как в security-специалиста. Инвестицию, которая 100% окупится с лихвой. Почему так? По последним исследованиям в мире, в принципе, Украина не является исключением. Мы переживаем все то же самое, может быть, даже в сравнении с другими странами, нашими соседями еще больше. Спрос на security-специалистов на сегодняшний день сумасшедший. Он в 3 раза больше, чем на любых других IT-специалистов. То есть security-специалистов сейчас ищут в 3 раза больше. Если взять среднестатистического нашего клиента и заказчика, у них уходит где-то около 6 месяцев на то, чтобы закрыть позицию security-специалиста. То есть полгода компания не может найти хорошего специалиста. И недостаток кадров на рынке на сегодняшний день исчисляется уже миллионами. Поэтому, ребята, все в ваших руках. Это время и это мероприятие – это в первую очередь инвестиция в вас, инвестиция, которая окупится. Спасибо большое, хорошего дня, хорошего форума.
Дамы и господа, встречайте, евангелист безопасности, компания Redware, Паскаль Гиненс.
Morning, Ukraine. Happy to be here. It was March 2016. Microsoft set out to do an experiment. They created a chatbot that runs on Twitter. The idea was to have a bot that emulates a teenage girl and that would interact with people and talk with them where people would feel like they're interacting with a real teenager. Now, as they did so, they published a chatbot, and the idea was that that chatbot would learn as it interacts with people. So getting information from the people and getting smarter at giving better responses. Now on another side of the internet, in the darker corner of the internet, there were some trolls from 4chan who picked up on that idea. And they started chatting with the little bot called Ty. And as they chatted with them, in less than 24 hours, the little teenage girl got corrupted into a sex-crazed, Nazi-loving Trump supporter. That shows you the dangers of putting out AI and machine learning on the internet without knowing how it works. There's some challenges, there's some surprises. So that's an example of poisoning. Now before we get to that, let's go back a step and see how this relates to cybersecurity. Now I'm pretty sure everybody knows the cyber kill chain. And just not to go into detail through all the steps, but as you can see, there's plenty of opportunity where hackers are coming into our networks that we can find evidence that somebody is trying to do something malicious in our networks. Even so, that we have many entry points and many evidence that somebody is trying to break into our networks and trying to exfiltrate information and moving around our networks. It takes, on average, more than 6 months for companies to find out that they were breached. How is that possible with all that information that we have? We are sitting on a big pile of information. We have monitoring tabs everywhere. We have SIMs. We have security specialists looking at events, and still it takes us more than 6 months to find out that we were breached. And typically, companies will not find out themselves. They will know it when somebody comes to them with a ransom telling, okay, you pay up or we're going to publish your information. Or a security expert comes to them and saying, hey, there's private information from your website that's getting traded on the dark web. So how is that possible? Yeah, my slides are good here, but not there. So first reason. Okay, we're back. No, we're not on the right slide. So, now in security, what we're always looking for is to minimize the false positives. For people who don't know what a false, pretty sure that most of the people here know what false positives are. But a false positive means that you see something happening, you think it's an attack, or the system thinks it's an attack, you investigate it, and it seems to be a benign event. Or a customer connecting to your website, he's blocked, he doesn't have access to your website, but he was a good one, so he should have had access. That's a false positive. False negative, typically you won't see them. That means that somebody got through your defenses, got into your network, and there was no event popping up or nobody seeing that it was happening. So what are we going for in security? That is to minimize the number of false positives and at the same time minimize the number of false negatives, right? However, truth be told, false positives and false negatives are related to each other, and not in a good way. Meaning that I can tune the sensitivity of my detection in such a way that I have a minimal number of false positives. See it like a firewall where you say allow everything. All your customers will be happy, they will always get access to the website, 0 false positives. But at the same time, all the bad guys also have free access to your website and to your applications and your resources. So you have a high number of false negatives, attacks that you will never see and never be able to stop. On the other side, you could tune the sensitivity very high and say, okay, I'm not going to let any of the attacks through, I will detect every attack possible. See it as a firewall that's said to deny all. So it's going to be very hard to get in without you detecting that somebody's trying to attack you. but at the same time, your customers do not have access to your website or their resources. So the false positives will be through the roof. So the game that we have been playing in security for many years is that game of finding the right sensitivity where we have a low amount of false positives and at the same time try to minimize the number of false negatives. Because false positives, it's hard to handle. Imagine a security team sitting in a SOC looking through all the detections that are coming in. They have thousands of events, maybe more, per day to look at. It's getting boring, right? Okay. Not working again. Can you advance the slide, please? Okay, good. So there's something that we call anomaly detection. That's what the security guys in the security operations centers are doing. Now there's a couple of facts out there related to false positives that make them a bad thing for security. First of all, threats are growing faster than our budgets. We never have enough budget to hire enough people to process all the information that is coming in and to make sure that we are not under attack, that we were not breached yet. Second, even if we had enough budget, there's not enough people. There's not enough security experts in the world to fill up all the security operations centers. And it's getting worse. It's getting more difficult to find experts like you in the room, experts to search and research whatever events are happening on our networks. And then there's the data problem. We are in a very good place when it comes into gathering data. We have sensors everywhere, we have agents everywhere collecting information, centralizing it, bringing it together. We are sitting on a big pile of data, but nobody has time to look at all of it. So there's only one solution there, and that's automation. We need to automate the process of looking at all the events coming in at us, all the false positives, trying to filter as much as possible before the actual security specialist can go into looking into the events. Imagine you're one of those SOC experts and your daily job is you come at 8 o'clock in the morning, you open your screen, you have 2,000 events to go through. You go to the first 100 events, they were all false positives. What happens to humans? They lose focus. They get tired. They get bored. By 5 o'clock, maybe they did 500 events, so they have to work until 11 o'clock to finish the other 500. They'll leave your company pretty soon. Make their work interesting again by bringing down those 1,000 events to maybe 20 events. And 20 events that are much more interesting to research. Giving them more time to make better automation at the same time. So where do we find this automation? Solution will most probably come from machine learning. And we have been using it for quite some time already. And going forward, we hope that it will get better at helping us to detect faster and better malicious behavior in our networks and in our applications. Now first, we need to situate machine learning. There's a lot of talk about artificial intelligence, deep learning, machine learning, but how do they relate to each other? So there's one big common domain which is called artificial intelligence. Artificial intelligence is one common denominator that we all use, and technically it is correct to say that what we are doing is artificial intelligence, even if it's machine learning, because it's part of it. Now artificial intelligence is much more than that. The idea of artificial intelligence is to have systems that are aware of their environment, that sense their environment, and that are able to automatically adapt to whatever is happening. Such a system does not exist yet in security, at least not that I'm aware of. Machine learning are algorithms that are getting better at the task that they're performing as they are learning on the job. So the more data they see, the better they get at doing whatever they needed to do. And that's something that we have been using for quite some time now. Recently, there has been a new movement into deep learning, actually re-enablement, because deep learning is nothing new. Deep learning is something that started back in the 1940s when some scientists were trying to simulate the behavior of our brain. They took a neuron, they attached some wires to it, and they simulated what was going on in the brain. It's loosely based on the idea of the brain. It is not working like a human brain. It's loosely based on it. Now fast forward, that same technology a couple of years ago was revived. Why? Because at the time that they were looking at those systems, they were limited in compute power, they were limited in memory, but most importantly, they were limited in data. We will see during the talk that to fuel deep learning networks, you need a massive amount of data. And that is something with the start of the hyperclouds like Google and Yandex, Alibaba, Facebook, they sit on big amounts of data. And we're fueling them data. Whenever we take a picture and whenever we tag somebody in Facebook, tag his face on a photograph, we are fueling that machine learning system to get better at recognizing that person that we tagged. So we have lots of data, we have lots of computing power. So that revived deep learning and that enabled it to do things that we were never be able to do before. Now let's start with machine learning, and we typically refer to it to traditional, even though that the deep learning already existed since the 40s. But with traditional, I mean everything that is machine learning except the whole deep learning and neural networks part. Traditional machine learning is about statistics, inference, and the problem it solves are typically the low to medium complexity problems. The problems that we humans can wrap our brain around and we can make a model of it. So whenever you have a problem, think about TCP, the TCP protocol. There's a contract. It's called an RFC. There's a state diagram that describes exactly how TCP behaves. Based on that, we can make ratios of how many SYNs, SYNACs, ACKs, resets, and FINs we need to see in a typical environment. Now the ratio of the number of SYNs and FINs or ACKs and SYNACs will depend on your environment itself. Because if you are in a transactional environment with many small transactions, you will have lots of SYNs. If you are in a streaming environment where you stream video, you will have only a few SYNs and SYNACs. So algorithms are able to model what they should be seeing, or that should be happening, but at the same time they need the data of the environment to fine-tune the algorithm to find the anomalies with a good performance. Now because we can wrap our brain around it, we need only limited data. So we're going to learn and we're going to use that data for baselining in peacetime. Since it's a model that we constructed and reprogrammed it in code and we know exactly how it behaves, we also know how big the rate in false positives will be. And we can minimize the rate in false positives. Now of course our world is not built from low and medium complex problems. There's many more high complexity problems out there that we don't know how to solve. At least as a human, we cannot wrap our brain around it. Think about all the traffic that is going through your network. Somebody asking you, write me code for a model that can simulate all the data on our network and that can find whenever there's a packet that does not match your model, whenever there's an anomaly in that. It's impossible. Applications are getting added. It's too much complexity. We cannot build that model. Maybe you can, but by the time you build it, the environment changed so much that you have to change it again. So we need a black box that we can code, not based on lines of codes or methods, but something that can be coded by example. So here we're going to take a box and we're going to train it using real life data samples. So we take a history of data samples, we put it in that box, we train that box, and then we show it real data from the network, and that box will be able to say, oh yeah, that resembles something that I've seen before, so that should be a good packet. Or it says, oh, that I never saw before, that I need to flag, that will be an anomaly. Now that black box is a neural network, a deep learning network. And you see one depicted in the middle. A deep learning network is first trained. So first you will give it data. So on the left side, on the red dots, you will feed in information. It will go through that network. And that network consists of neurons, very basic elements. It's not rocket science. One such neuron is just a function. It has input links coming in. It will take the sum of all those input links with a coefficient on every link, run it through function, a function that can be linear or that can be nonlinear, and then will come an output, and that output is fed into the next layer of neurons. It's very basic. One element is very basic. But there's many elements working together. There's many links. Now to train a network like this, what we do is we present information on the left side, on the red side. And then we look at the result. So that means, wait a minute, so you present information, you get a result, but you need to know what the result was up front. So you need data, labeled data. We call that supervised learning. So you give it, for example, images of cats and dogs. You give it an image of a cat, it comes out, I think it's a dog. You say, no, it was a cat. So what you do is you go back in that network from right to left, and you're going to change, what can you change? The coefficients on every link. And you're going to adapt it until the moment that that picture that you presented that was a cat comes out as a cat. You put the next picture, again a cat, it says dog. No, it's a cat. So you're going to change, again, all the coefficients. Now this comes very close to something that we all know in a two-dimensional world, which is curve fitting. Finding the best curve that approximates all the points. Actually, deep learning, deep neural networks are very difficult constructs, but what they do basically is building a multidimensional plane that approximates the points that we are feeding into it. So the only thing that it does is minimizing the error between every image and label that we know. So we're going to have that training set, we're going to build a network, and then we're going to feed it real information. So a new image that we don't know yet if it's a cat and dog. We will feed it in, and it will look, does that point come close to that curve, to that multidimensional plane of a cat? Okay, it will be a cat. If it's closer to that one of a dog, it will be a dog. That's how you look at deep learning networks. So you have that black box, that generic network that you can train. Now the problem is you need lots of data to train those networks. You'll see in a second how many, but it's a lot of data that you need. And it needs to be good data. It needs to be labeled, which might be a problem in certain areas. Some areas we have labeled data, other areas we are still lacking lots of labeled data. So bringing it all together, detection algorithms will either consist on the left side something that is deterministic, transparent, which is the traditional machine learning, something that we built as a human. We coded it in real code and we know how that model works. However, it's limited to low and medium-sized complexity problems. On the right side, we do less with code and we start to train a generic model using data. So now you need lots of data and you're going to code by giving it examples, feeding it data. But this seems like a really great idea. So why don't we just forget about all the traditional machine learning and do everything with what we did on the right side, everything with the algorithms on the right side, the general networks, because it can solve pretty much any problem, right? Now, there's a number of challenges with deep learning. First of all, as I said, we need a lot of data. Where do we get that data? We can create synthetic data. We can say, okay, I have a couple of samples here from network data, and I'm gonna make myself data from it. So I'm gonna make small permutations that I know are correct, and I'm gonna feed it into the system. Not a good idea. Because the data that you are creating, it's correlated. The system will find some correlation in there. It will never work well. You need real life data, and the big problem is that real life data needs to be tagged. You can train it on the go. You can say, okay, I start with a small set of data. It will be a bad performing system. And every time something comes out, I will have a human look at it and say, okay, that was correct or not correct. That's basically the idea. And as you go forward, as the human is tagging it good and bad, it will get better and better and better. Now, if you can start with a big set of data, you're in a good place, you have well-performing network, you still need a human out there to find out if it's good or bad. Because sometimes those systems, they make strange choices. And nobody can explain why this happens. So transparency, they're not transparent. Even to the point that some big CRM vendor who is using AI and using a deep learning system to give sales a recommendation on certain people to visit because it will maximize their potential to get business. So they had an AI system, they looked at all the parameters inside the system and they said to the sales, go visit this guy. You have a very good opportunity there, you will make business. The sales guy knows his business, right? He tells, no, I don't agree with that. Why do you make that decision? Actually, they go back to the CRM company and say, why do you make that decision? Well, no idea. It just comes out of the system like that. We trained the system, it works like that. Always been working good. So what they started to do is build a second system. What they did is they take their trained deep learning black box, they put an input to one, you know, like you do circuits, black box circuit testing. Put one input to one, look at the result. Put the second input to one, look at the result. Try to figure out how it works. And they made a decision tree based on that whole reversing of that black box. So now they have two systems. One system is to actually find the good prospects. The second system is to explain why probably that system came to that idea in a decision tree, so that people could understand what is going on. That is like trying to reverse engineer that black box. Because even though that all those small elements are so simple, it's very complex as a human to understand all the interactions that are going on all the time inside that whole network. It's too complex for us to understand, and nobody has a full grasp on what is happening. There's some research, give that, but there has been no definite answer. There's also many models, and deep learning is like engineering. You know, you have scientists and mathematics on one side, which is deterministic. Engineers are more like the guys, do it like this. Because I know from experience, this works well. So they will see a problem, they will look at data, they'll say, oh yeah, we're going to use that type of deep learning network. Comes out very bad. Well, we can tune it a little bit. We're going to add a layer like this, and we're going to remove a layer there. And test it again, and try. So it's trial and error. It's not an exact science, it's a feeling. The other problem, learning in changing environments. Whenever you add an application, you're adding more entropy in your data. You're adding more complexity, more diversity in your data. We will see this when we come back in curve fitting. Remember your curve fitting. If you find a good curve, but suddenly you add more points, that curve will not fit anymore. You have to refit the curve. And sometimes you have to tune the complexity of the curve. Sometimes a line was enough. Sometimes you needed a second order polynomial. Sometimes a third order. Sometimes nth order polynomial to well approximate the data. So every time you change something in your environment, you need to retrain the whole network, and you need to look at how effective it is. If it's not performing well, you may need to change the complexity. Either it's too complex or not complex enough. That brings me back to the training data. You don't need only data for training the network, but also for testing it. So typically we will have an 80-20 rule. 80% of the data will be used for training the network, 20% will be for testing the performance. So you train it with 80% of the samples, and then the leftover samples you use to look at how well it is recognizing something when you give it the input without knowing the output. So that will enable you to see how well your network is performing. And then of course we saw with little Ty that in some contexts it's more difficult to learn than others. When we put it in real production, in real life, we are sitting in an environment where people are attacking us. So we are learning attacks. We better not take those attacks as good things, because otherwise we will learn to see attacks as good things. And we will reuse that like little Ty did. So we need lots of data, and good data. Here's some examples to give you an idea of how much data you need. For a state-of-the-art speech recognition system, you need about 100,000 hours of audio. If you would play that sequentially, that's 10 years of sound. But not only the audio, remember you also need the transcript. Somebody had to type the transcript of the audio so that you can make the match between audio and text. So whenever you go to YouTube, you have those subtitles, you have pretty much an idea what's happening behind when you see those subtitles. It's a system that has been trained with hundreds of thousands of hours of previous audio produced by people who put in subtitles, 10 years of that data, and based on that, they trained a generic model, a deep learning network, to be able to recognize whatever speech they see now. So when you play now a YouTube video, you can enable subtitles in English, for example, and it will give you the subtitles in real time based on what the person is saying. Face recognition, 200 million images. For state-of-the-art system, you need about 200 million images. Tagged images. Yeah? So if you want to recognize the face of a person, those images need to be tagged with that name of that person, otherwise it's useless. The only thing that you can do with deep learning and machine learning with data that is not tagged, we call that unsupervised learning, is finding structure, like classification. Finding clusters of similar data in that big giant pool of data. That's typically what you can do. With supervised learning, you can do much cleverer things, but you need the tagged information. Now I talked about complexity. Whenever you add an application to your network, there's more diversity in your data. Maybe your curve will not fit very well anymore. You need to adapt the complexity. Here's the depiction. You see on the left side, you're trying to approach the data samples with a very simple linear line. Not enough complexity, it will not perform well. Well, you say, I increase to maximum complexity. Then you come on the right side. So on the right side, over there, you see a high order polynomial that goes straight through all the points. Now for us it's easy to see, yeah, this will not work very well. Because whenever you have a point that sits somewhere, I'll try to show it, here, that would be a good point. Yeah, everybody agrees that this follows the trend of the points. However, in this model here, the error will be very big because it's a long distance from what we model. It's a bad model. Why? Because it has too much complexity and it will actually fit the noise. The idea is that you cannot fit the noise. Now many researchers fall in that trap. They make a deep learning system, they put in training data, and when they go through the training, the idea is to minimize the training error. All goes well. They fit to zero error. This is a fantastic system. Zero error. We 100% fitted all the images. First time they show the real image, they show a cat, it says giraffe. What happened? Well, if you fit that noise, well, it's going to work very well for the points that you have because they you have just thrown a curve through all the points. It will work perfectly for all the points, but it will be very bad whenever you give it a new point. You need to find a good middle, and that is where you find that prediction error So when you use your training data, you train the model to minimize the error. So you can train until the error becomes completely zero in the complexity. But if you use your test data, you will see that the prediction error goes up. So you have your curve of prediction error. As you move through complexity, there will be somewhere a good minimum where you have a good training error, but at the same time, whenever you present new samples, that will also minimize the error on the samples. And that's the good point where you need to be. Now, why do I tell all this complexity? Just to make you understand, this is not hands-off. This is not something that I give you a box and I tell you, this is a deep learning network, go and deploy it in your network. It will learn and magically it will do the job. It doesn't work like that. You need engineers, you need people who understand this, you need people looking at this network all the time. You need to tune it. So remember little Ty, an example of poisoning. Those are things that can go wrong. Whenever you have something that works well in the lab, you put it in real life, surprises might happen. Yeah, and I had to edit most of the words in there. This presentation also used in the US, so there's censored a little bit. But there's a link on the bottom, and I'm sure the presentation will be shared. So there you can find the original pictures that were grabbed from Ty when it was happening. Another kind of attack, adversarial attack. Remember about fitting the noise? The idea is we cannot fit the noise, so we're going to make it less complex, not fit noise. So we're going to remove the noise. Now what if you add some noise? So take a picture of a sports car. So the picture on the left side is the original picture that you presented to your deep learning model. And it comes out as a sports car. You add some noise to that image. The right image is the image, the original image with the noise added. For us as humans, we see immediately, it's the same picture. That's a sports car. Well, you feed that image to the same model, it comes out toaster. Sylvester Stallone, add some adversarial noise, comes out as Keanu Reeves. Of course, that's all fun, it doesn't hurt us. However, bring that into the world of automation and cars. You have a self-driving car. The self-driving car has a deep learning network that is able to find traffic signs and recognize those traffic signs, and those traffic signs will give feedback to the car what it needs to do. So whenever a car comes up to a stop sign, it recognizes the stop sign, it knows it needs to slow down to that intersection and stop. And then look left, right, and then go on and drive. Now, if you put some noise on that stop sign, and there were some scientists that discovered this, they put some stickers in very specific places, so adding noise to that stop sign. And suddenly, the car, or the system in the car that needs to interpret those signs, interpreted this as a 25-mile-per-hour sign. So the car is coming up to the intersection, and instead of slowing down and stopping, it's speeding up and driving right across. Because it was thinking that this was 25 miles an hour, not the stop sign. That's an adversarial attack. So now that we know pretty much what deep learning can do and what the challenges are, there's lots of good things that we can do with it, and we will come back to it in a second. But first, whenever there's good, there's bad. We all are very much aware of the bad guys that are out there. So they are following our research, and they typically pick up very fast on the new things. So they have already a way to weaponize machine learning. So how can they use it? Now, some of them are still scientific research, but one of the things is increasing the evasiveness of malware, the evasiveness of command and control communication by using what we call generative adversarial networks. What are those GANs? So we call that a GAN. What is that thing? Simple. Deep learning network here, deep learning network there. This deep learning network will generate data. This deep learning network will try to figure out if this is good or bad. So you have an executable, you feed it into that generating, that noise adding network. It adds noise, and then the detection network says, oh, this is malware, and feeds it back. Someone said, oh, you know that it's malware. Okay, I need to change a little bit. I need to tune the noise. And I will do this loop, and I will automatically tune the noise on that executable until the moment that the detection network cannot detect it anymore. So you automatically create malware that is undetectable by any detection source on the world today, even the ones that are based on AI. And same for DNS generation algorithms. You know, the ones that change DNS like 10,000 times per day just to evade whatever control you might have to block or blacklist malware. The other thing, spear phishing at scale, and we will come to that in a second. But first, let's talk about CAPTCHA. You know, those annoying things that pop up before you get access to a website, supposed to recognize a human from a machine to protect the website from bad robots, bad bots, trying to do malicious things with the website, like scraping or ticketing or inventory stealing or scalping. So CAPTCHA, and whenever I see that CAPTCHA, especially the one on the bottom right, like 50% of the time I miss it, right? It's like really bad. I hate it when that pops up. In 2012, there was some traditional machine learning. Support vector machines are what we call traditional machine learning. 82% accuracy. 2016, the bottom one, we got with deep learning, they got 98% accuracy in breaking CAPTCHA. 98%. I, a human, maybe get 50, 60%. So what's the story here? Tells you that machines are actually much better at getting through CAPTCHA than humans. So something that was there to stop machines and only allow humans is actually doing quite the inverse and annoying me at the same time. Now, I'm not saying that every bot is equipped with that kind of complexity, but there are bots out there who can run and who can get through CAPTCHA very efficiently. That's why also Google changed CAPTCHA. So the latest version, I believe it's version 3, is now using behavioral tracking. It's not using images anymore to show you, click on a coffee or click on all the images where you see a bike or a storefront. No, it's just trying to see what is the intent of the user and trying to encode that and find out the difference. So the world, as you see, the world is moving more from one single point of access, one single decision into behavioral. Looking at what is the behavior, what is the intent, make decisions based on that. Social engineering, spear phishing. You all know spear phishing? Hackers look at information from a company. We have lots of information out there. When you're a publicly traded company, you have every quarter you have a financial statement with lots of information. There's project names in there. There's names of the CFO, CEO. So a hacker investigates, takes that information and says, okay, I'm going to craft an email from the CFO to the CEO, or vice versa. They're both as bad in recognizing phishing. Doesn't really matter. So I create an email from one to the other, and I put in the name of that one of those projects from that financial statement. Automatically, people associate that project. Oh, that must be somebody who knows internally, so that should be okay. So our brain focuses on this and says, okay, I'm going to open the attachment. Bang, you're phished. Now, it takes a lot of effort to create that phishing. Yeah? Now, using deep learning and using natural language processing, attackers are now able to automatically scan the internet, scrape the information, run it through their algorithms, and do spear phishing at scale. So phishing, before we had phishing was large scale. Yeah, you had one email, you send it to millions of users, but the click rate or the open rate of the attachment is very limited, a couple of percent. Spear phishing, very high likelihood that somebody will open the attachment. However, lots of time and effort. Now with machine learning, we automated that. So suddenly they can do it at very high speed. So where do we use machine learning in security? And since we're hosted by Cisco, we'll start with the Cisco example. Cisco has some engines that are able to look at traffic, encrypted traffic, and detect malicious information in that traffic. And actually, I believe that this system is running right now. So Whatever you do, take your phone and download malware. See if it works. If it doesn't work, I didn't tell anything, right? But that is based on machine learning. So what they have lots of samples of known malware traffic. They have lots of samples of good traffic. And they put them in those black boxes. They train those black boxes. There's multiple of them. Don't look at the world like I told you, well, there's a black box and you put information in it and out comes something magic, a decision. It's not that simple either. So you have to put multiple boxes. First of all, you need to sanitize your data. Remember Thai? If somebody says, fuck to Thai, well, just make a filter that eliminates all the offensive words like fuck and crap and whatever. Take them out before it starts learning. Easy. So you need some filters, you need normalization of data. You can have multiple stages. So you can have one deep learning system that does this, and based on that result, you will trigger another deep learning system that does something else. You will have traditional machine learning in the mix there that does the clustering that brings them back together. So it's not like it's one system. It's typically a pipeline of analytics. Formatting, normalizing the data, processing it in one way, coming out with something, enriching information, going to the next stage. So it's like a pipeline of things that are happening. So they have a couple of machine learning algorithms that are running on that data that are able to recognize whenever there's malware in encrypted traffic. And if you want to see it working, as I said, download some malware right now on your phone and you will see if it works, because it's running right now on the Wi-Fi. So I have been told. If it's not, well, your phone will be infected. Sorry about that, but don't take me liable for it. Another example. You know the good bots and bad bots? You have an online website. You want to allow humans. We can do human detection versus machine. Now once you know it's a machine, well, there's some good bots out there that are doing price aggregation and indexing like Google. So you want to leverage the good bots to have people come to your website. But at the same time, there's bad bots out there who are trying to scrape your information, who are taking all your inventory so that there's nothing in stock, who are jumping the queue whenever there's a ticket sold, and jumping the queue and no human can buy a ticket and concerts are sold out in 5 seconds. Hey, nobody can check out in 5 seconds, going through the MasterCard details and whatever. Nobody can do that in 5 seconds. Still, they're selling out in 5 seconds. Robots can do it. They can jump the queue. So to detect those, because they are coming at such a complexity and using such complex algorithms now, the bots that they mimic the users, we have to look at how they behave. Once we know how they behave, what their intent is, we can classify them as a good or a bad bot. However, now they also have those lots of IoT devices where they can hide behind. So instead of coming from one source, they're coming from 100,000 different sources at the same time. And we don't know which one is the same bot, so we need to cluster them, bring them together with unsupervised learning, and then do some supervised learning to recognize the typical intent patterns, and based on that, we can classify them as good as bad. If we're not sure that they're good or bad, we can send a feedback like a CAPTCHA, for example. If the idea was to recognize a human, we send a CAPTCHA, we feedback that information into the network, we learn it, we make it better and smarter to get, in the future, a more better decision. Same, account takeover detection in the cloud. Accounts are your number one keys when it comes to the cloud. Whoever has access to the admin account of your cloud can do everything with your infrastructure out there. So account takeover is very important. You can do detection looking at API usage of a user. You can map them out and you can see anomalies in those APIs. Which one is he using typically? If he uses another one, it's not normal. Geography. Put in geography from where he's using that API. And then you can augment that detection. So, for the people that just joined us, or for the people who are not interested in all the details, the summary. We protect our networks. We do it today with devices that sit close to the networks. And typically what you will do there is use some real-time detection and real-time protection. That will be based on traditional machine learning. Low false positives modeled very closely to the problem. However, there are some very clever, sophisticated attacks that will go through it. So we can add layers. And we will add layers with known attacks that were detected by systems in the cloud that crowdsource information from many companies, go through that data, bring out some analysis, then there's a human looking at it, creating a signature, and feeding it back to the device. You can also use deception data. Have honeypots around the world, find attackers that are trying to attack those honeypots, run analysis on it, take out the ones that are most important, put them in a list of IP addresses that are the most active attackers today. And then you can also go one step further and do, like also Cisco does with Umbrella, look at all the DNS and URLs and look at what is good and bad behavior, take that information from the whole world, and whenever you learn from that, everybody will be protected by what you learn from every individual in the world. So this is going from traditional machine learning to more complex systems that are running in the cloud. Remember, you need lots of data, training takes time. The detection phase does not take that much time. It's just a network, you put in an image, you go through the calculations, you get there. It's limited in time, pretty fast. But the training is what takes a lot of data, a lot of memory, a lot of time. So the training is typically done in the cloud. You take the result, put it in an agent on a machine. You can do malware detection using an agent that runs on a desktop. But you don't do the learning there. The learning happens in the cloud. So there's a delay between them. Between retraining that model, doing the detection, and having it imposed over here, mitigated in that point. So that's what we can do with threat intelligence feeds. So typically you will do the more complex things in the cloud, find the information, feed it back to the machines that do the mitigation on site. So looking ahead in the defense, short term, we're already using it, anomaly detection, research and malware. We use those systems to try to recognize what is good and bad and what they're doing. Sophisticated attack detection and threat intelligence. Now we're looking at the longer term, automated defense systems. You put the system there, it will learn and it will get better at what it's doing. It will adapt depending on your environment to protect you automatically. It doesn't exist today, it will come. The threat on the other side, it's always in lockstep. Good and bad is always in lockstep, so the threats are always there. Short term, they're already here. Automated attacks. Hackers are getting ever more automated. Their attacks more complex. The humans are still creating the attacks though. Still an attacker that does it. And mainly we see improved evasion. So using DGAs, using anti-malware that is obfuscated. Long term, well, we have automatic defenses. They will have autonomous attack systems that automatically find, do the fuzzing, create new attack vectors, try those attack vectors, and they will automatically attack us. And we will need automated defense systems. It's always going in lockstep. So, summarizing, machine learning is already defending our networks for quite some time already, the traditional machine learning. We know that attacks are getting more sophisticated, more automated. We know that detecting and stopping those attacks will require some intelligent automation. We're not fully there yet, but we know that that automation will come from something that evolves out of machine learning, and more specifically, I think that the deep learning will be the important part going forward. Thank you.
Ну, в принципе, подожди, сейчас это не показываю. А вот что здесь написано? О, вот это, да. Выводим? Выводи. Стопэ. Так, не расходимся. Сейчас быстренько.